Hello class. This video clip is designed to replace the recording that we lost on Friday afternoon. So I'm going to very quickly summarize the work that we did in this video. So the first thing we looked at as part of topic 6 is computer arithmetic, and I've decided that we're going to have a look at number bases and number conversions. And what I mean by number conversions is simply how to convert a binary number into a decimal number and vice versa, and how you can convert a binary number into a hexadecimal number and vice versa, and how you can convert a decimal into a hexagonal, and so on. So the methods I'm going to show you are effective and fairly straightforward. But they're quite important, and I guess sort of one of the questions I want to ask you is, why do you think binary numbers and hexadecimal numbers are important in computer science? Well, from topic 2 on computer architecture and instruction execution, we learned that it's vital to represent programs which are simply sequences of instructions by means of sequences of bits, typically 16 bits. So you can use 16 bits to represent a computer instruction that is actually understood by the computer. And I'll come back to that a bit later on. So we're going to have a quick look at how number bases work and what they are. And first of all, we're going to convert binary numbers to decimal and vice versa, and then we're going to convert decimal numbers into hexadecimal numbers. Okay, so here we go. Background, which you may or may not be familiar with or have thought about very much, or have never had reason to consider it, is that a bit stands for a binary digit, so BIT. And you can think of a 0, which is a binary digit, as representing an off state, and 1 for a non-state in terms of, say, electrical signals in a digital circuit, or maybe logic 1 or logic 0. Or you can think of binary digits as representing the presence of 5 volts, or the presence of 0 volts. And the point about a binary digit is that each digit is either a 1 or a 0. It can't be both, and it can't be neither. So strings of 1s and 0s can be constructed in order to represent anything you want: text, sound, video, your weight, whatever it is. You can always represent data by means of a mapping into a sequence or sequences of binary data. And it's worth remembering that a binary sequence can be transmitted within a computer at very high speed. I mean, possibly 4 billion bits per second within the computer, if it has a 4 gigahertz clock, or a 2 gigahertz clock, 2 billion bits per second. And there are certainly computers around that can transmit data far faster than the figures I've just quoted. So that's fast, and it's a massive amount of data. So second thing I want to draw your attention to is one binary bit can have 2 permutations, 2 values, 1 and 0, not at the same time, and always 1 at a given time. 2 bits can have 4 permutations, combinations: 1 1, 1 0, 0 1, 0 0. And 3 bits have 8 permutations, starting with 1 1 1 and ending with 0 0 0. And given any n bits, those bits have 2 raised to the power of n. That should be a capital N, by the way. 2 raised to the power of n permutations or combinations. And therefore 4 bits would easily allow us to represent the each and every element of the English alphabet, all alphabetical characters. And I think I'm right in saying that there are exactly 26 characters in the English alphabet. But there are more characters. There's punctuation marks, special characters like the percentage sign, the forward slash and the backward slash, and the sign for division, and so on and so on. If you were to use 8 bits, then you could represent 256 different numbers. Or if you had a vastly complicated language, and I'm not quite sure, I don't know very much about the structure of one of the Chinese dialects, but you do get a very large number of combinations of, or configurations of characters within the language. So 8 bits, that's 2 raised to the power of 8. 256 different numbers. 10 bits, you get 65536 permutations. And with each permutation, you could certainly represent a meaningful item of data if you want to interpret those bits in a particular way, according to some convention. 32 bits, 4 billion permutations, and so on. I mean, you might want to think about what I think I call an exabyte in the next character. How many permutations does 2 raised to the oh well, we'll consider that a bit later. Just skip that for a moment. Right. Third element of a background I want to give you is that a kibibyte is the name for the number 2 raised to the power of 10. A mebibyte, 220, 2 raised to the power of 20 bytes. A gibibyte, 2 raised to the power of 30 bytes. A tebibyte, 2 raised to the power of 40. It's quite a big number. Right. Kilobyte, as you probably are aware of, is just 1,000 bytes. Kilobyte, 1,000 bytes. Megabyte, 10 raised to the power of 6, so that's 1,000,000 bytes. Gigabyte, 10 raised to the power of 9,000 megabytes. A terabyte is 1,000 gigabytes. And check out what this is. How many bytes in an exabyte? Can you do that? Is it 10 to the 18? It's a very, very big number, and it's an interesting exercise to try and give a number to a particular set of things. I mean, is there anything you can think that is as big as an exabyte in terms of number of bytes? I mean, can you imagine how large that particular number is? Right. So number bases, and the convention of representing a particular number with a particular base is to write the base as a subscript. So 43 decimal is written technically as 43 to the base 10. This binary number has a base 2. This hexadecimal number has a base of 16. And as we'll see in a moment, I mean, what this actually means is that this number is equivalent to 4 times 10 raised to the power of 1 plus 3 times 10 raised to the power of 0. I mean, a number raised to the power of 0 is always 1. So 43, the decimal number 43 can be explained in terms of a sum of powers of 10. just as this number, this binary number, is actually equivalent to 1 times 2 raised to the power of 0, 1 times 2 raised to the power of 1, plus 0 times 2 raised to the power of 2, plus 1 times 2 raised to the power of 3, 8. So it's 8 plus 4 plus 1. That's 13, I think. Right, so this hexadecimal number you can think of as being 7 times 16 raised to the power of 0 plus, well, what? Let's suspend analysis of this number until the next couple of slides. So let me say here, a hex number, okay, so it's a number with base 16, uses all the digits between 0 and 9, together with the letters A to F. So A, the hexadecimal number A in decimal terms is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. So the other thing I want to say about hexadecimal numbers is that any hexadecimal number can be represented by 4 bits. So for example, you know, the decimal number 10 can be represented by 4 binary bits, and A can be represented by 4 binary bits, and the number 2 can be represented by 4 binary bits. Right. So for example, the hexadecimal number 1e is actually equivalent to 30 as a decimal number, decimal number 30. And the actual binary equivalent to 1e is 0001, so that's the first 4 bits representing 1, plus the binary number e, which is, I think I've already said, can be represented by the binary number 111. 1110 is equivalent to E in hexadecimal. So if you put those two numbers together, 1 and E, you do get this 8-bit sequence of binary numbers. And if you care to work it out as a decimal number, you've got 1 times 2 plus 1 times 4 plus 1 times 8 plus 1 times 30, 1 times, no, it's 2, 4, 8, 32, is that right? No, I'm going to have to skip that. I have to think about that. What is this 5-bit number? What's it equivalent to? You've got 0 times 2 raised to the power of 0, 1 times 2 raised to the power of 1, 1 times 2 raised to the power of 2, 1 times 2 raised to the power of 4, and 1 times 2 raised to the power of 3, which is 8. So I think that probably does actually come out. I'm not going to try and add it up whilst I'm giving this talk, but you convince yourselves that 1e is actually 30. Why? Well, 1e is actually equivalent to this binary number, and we can compute what the equivalent to this binary number is in decimal. Okay, so let's go forwards a little bit. So the concept and practice of converting numbers from one base to another can be seen formally by considering the following. So once again, so I'm putting this in black and white. 2098 in decimal is equivalent to 8 times 1, so you've got an 8 here. So 8 times 10 raised to the power of 0, which is 1. And it's 9 times 10 raised to the power of 1 plus 0 times 10 raised to the power of 2 plus 2 times 10 raised to the power of 3. So here's a classic example of how you're analysing a number to a particular base in terms of powers of numbers represented by powers of that base. So it's 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3. So have a look at this number, which is how many bits? 1, 2, 3, 4, 5, 6, 7, 8. And a little bit of work will actually indicate that it's equivalent to 1 times 2 raised to the power of 7. So I'm starting at the other end, which is 128, plus 0 times 64, plus 0 times 32, plus 0 times 16, plus 0 times 8, plus 1 times 2 raised to the power of 2, which is, whoops, let me get this page back. Let me just say that again. This is 1 times 2 raised to the power of 2. So I say that again for the second time. This is 1 times 2 raised to the power of 2, which is 4. And then you've got 1 times 2 raised to the power of 1, which is here. It's just 2, plus 1 times 2 raised to the power of 0, which is 1. So if you add all those together, you should get 135. And this is incorrect. So let me just correct this. This should be not 2. Let me try and cross that out. It should be to the power of 10. Okay. So this binary number, you can see, is equivalent to 135. If you add 128 to 8 plus 4 plus 2 plus 1, you do get 135. But for goodness sake, check here to make sure I'm right. Okay, so this is a standard way of converting a binary number into a decimal number. So how about converting decimal numbers to hex numbers? Well, okay, so I'm going to give you the rule, and I think it's a two-step process. So first of all, you convert your decimal number to a binary number, and as a second step, you then convert the binary number to a hex number. So let's work it out. Let's do this. All right. Let's think about 211. And I'm going to compute the binary equivalent, which it turns out is 110100011. And you should immediately ask, well, how did you get that? Well, the answer is that you divide the number that we started with, 211, by 2 repeatedly, and I get 105 with a remainder of 1. Okay, and then I divide not 155, so that's wrong. You divide 105 by 2 again to get 52 remainder 1. So it's 52 remainder 1. and so on, and so on, and so on. So I'll give you a full example of this. So we get a sequence of remainders. Look, here's a remainder 1. The next division results in a remainder 1. And you terminate at some point after you've divided it until you can't divide the number anymore, but you've got all the remainders on zeros and so on. You simply reverse the sequence to get 1 1 0 0 1 0 1 1. So the idea is that you repeatedly divide the given number by 2 until you can't divide it anymore, and then you reverse the sequence you've actually obtained. And as a second step, you split the resulting sequence of binary digits into 2 groups of 4 bits. And then you convert these 2 groups into hexadecimal numbers. So if you remember, we had 1 1. Okay, let me just go back here. We had 1101 and 0011. So 1101 is actually equivalent, if you work it out, to the hexadecimal number D. Right? So I'm not going to convert it to decimal and prove that to you, but D is actually equal to 8, 9, 10, 11, 12. And the second group of 4 digits is actually 0011, which is 3. So what I get is D3. Right? D3. Okay? So just work through that and convince yourself that you understand the technique, and the calculation of the equivalent is in fact D3. This number is equivalent to D. These 4 bits are equivalent to 3. And if you wanted to, you could say translate D3 back into these 2 hexadecimal numbers and recompute the decimal number from which the sequence was converted, and you will get the original number, which I think was 211. So I'm sorry about sort of not making this little part absolutely clear. So think about in more detail. So we've looked at a quick magical conversion of a decimal number into binary. I'm going to have a look at the conversion of 98 decimal into binary in some detail. So let's have a look at that. So 98 is a number that we've got to convert into binary. Divide it by 2, you get a remainder 0. Got 49, divide that by 2, you get 24 remainder 1. 24 divided by 2 is 12 remainder 0. 12 divided by 2 is 6 remainder 0. 6 divided by 2 is 3 with no remainder. 3 divided by 2 is 1 remainder 1. And finally, 1 divided by 2 gives you 0 remainder 1. So this gives me, if I can move the page down a little bit, this gives me the sequence 0 1 0 0 0 1 1 0 1 0 0 0 1 1. Now the rule says reverse this to actually get the conversion. So what we get by reversing this sequence, this is the sequence we're reverting, we get 1 1 0 0 0 1 0. And if you mechanically check what this number is in decimal, you'll get this. It's equivalent to 64. One lot of 64. One lot of 32. 0 times 16. 0 times 8. 0 times 4. Plus 2. So 64 plus 32 plus 2. And that gives you the number that we started with, 98 here. Okay. But there is an alternative, which to me is slightly more intuitive than calculating what possibly might be a very long sequence, and then reversing the number to get the conversion. It's to do with repeated subtraction of powers of 2 which are less than a given number. So supposing we wanted to convert 363 decimal into binary. So what do we do? Well, I'll give you the first few steps. 365. Well, you can take this number away from it, 256. And notice that 256 is 2 raised to the power of 8. Okay, so I'm going to do that. I mean, I can't take 512 from 363 because I'd get a negative number. I just want to repeatedly divide powers of 2 from 363. So there's another step or two. I think I've missed one out here. And we get 43. And 43, well, you can take 30, you can't take 64 from 43, but you can subtract 2 raised to the power of 5, 32 from it. And that, if you do that, it leaves you with 11. So what power of 2 can you take away? What's the biggest power of 2 you can take away from 11? Well, having a look at the table, you can take 8 from it. You can't take 16, which is 2 raised to the power of 4, but you can take 2 raised to the power of 3. No problems. So take it away. You get 3. Then you're left with 3. And then what's the next power of 2 that you can take away from that? Well, it's actually 2 raised to the power of 1. 2. So I'm going to take 2 away from 3. I'm going to get 1. So let's have a look at this. You can check the result more or less by saying, well, okay, take away 2 raised to the power of 8 from 63. Now take 2 raised to the power of 6. Now take 2 raised to the power of 5. Now take 2 raised to the power of 3. And now take 2 raised to the power of 1. And that actually leaves you with 1. Now take away 1 and you should get 0, and you do. So, I mean, putting it, just swapping all these expressions to the other side, 363 equals 2 raised to the power of 8 plus 2 raised to the power of 6, all the way down to 2 raised to the power of 0. And that gives me, this optional rule gives me a lot of confidence in the rightness of the technique. And you can check by working backwards. So what we actually came up with, you know, all you're doing here is that you're adding all these numbers together. In other words, you're looking to see what number is, what decimal number is given by 1011101011. And you can see that it's 256 plus all these factors here. That does actually give you 363. So what I haven't made explicit here is that simply that I managed to take 2 raised to the power of 8 away. So that corresponds to this 1 here. I can't then take 2 raised to the power of 7 away, so I've got a 0 here. But I could take 64 away from the result of taking 256 away. Those 2 to the power of 6. Though this is 1 lot of 2 raised to the power of 6, and so on. That's where I got this binary number from. This is the equivalent. So, I mean, let me know if you have any problems with this. So, finally, I want to show you how to convert, in 2 steps, a hex number to decimal. So we use a rule to the effect that you first of all convert a hex number to binary numbers first, remembering the fact that any hexadecimal number has a 4-bit binary equivalent. Then you convert the overall binary sequence to a decimal number. So the question is, what is 2A3? So that's a perfectly good hex number. What is it in decimal? How does it convert? So let's do that. Using the technique above, I mean, we're converting a decimal number into binary. We would actually get 001010100011. So it's a 12-bit binary sequence, and the first 4 bits are equivalent to hexadecimal 2. The next 4 bits, 1, 2, 3, 4, 1, 2, 3, 4, is equivalent to A. This binary sequence 0, 1, 0, 1 is equivalent to A. Remember that A in decimal is 10, and this binary, these 4 bits, actually give you 8 plus 2. Okay? And the final 4 bits gives, in binary, is 3. So 3 in binary is 0, 0, 1, 1. And if you now convert that convert the sequence, it's entirely possible to convert that into a decimal number. It should give you 675. And again, just to remind you, I mean, this is 1 time, it's equivalent to, this 1 here represents 1 times 2 to the 0, in other words 1. That represents a 2, and so on. These all represent powers of 2. So 1, 2, 3, 4, 6, 7, 8, 9, 10. 2 raised to the power of 10. Okay. So just check this. Make sure you can get this equivalence relationship out. And that's all I've got to say formally about conversion. And it seems to me it's relatively easy. And you need to practice conversions a little bit, because for the next assess coursework you'll be asked to do some conversion of numbers to various bases. And the only other thing I want to say at the moment is, the only other thing I want to do is to ask you the question, why do you think hexadecimal numbers are important? Why are they used, in other words? I mean, I think we should have an understanding of why binary numbers are used in computer science, because you can represent information like instructions or data very easily by means of binary sequences, which you can used to, as it were, talk to a computer system, or you can program a computer system simply by specifying a program in terms of ones and zeros, as we'll see a bit later on. I want you to, whoops, wait a minute, sorry about that. I want you to look at this sequence here for 4 seconds, and I'm going to count 4. 1, 2, 3, 4, and then I'm going to simply go up the document a little bit, and I'm going to ask you to tell me what those 12 digits were. And can you do it? And I suspect you probably can't. It's not exactly a memorable, easily remembered sequence. But can you remember? I mean, perhaps you'd be able to remember this number though, 2A3. This is a number that we're converting. It's far more easy to remember this 3-symbol number, 2A3, than it is for this 12-digit binary number. And hopefully you'll agree, but I'm sure some of you will disagree, and I'm sure some of you have got what's called an eidetic memory, and you can remember anything that you're shown. So, okay, so just going to pause slightly there whilst I... what am I going to do now? I'm going to, for the second part of this recording, I'm going to give you, I guess, I'm not going to give you any diagrams or anything, but it's a purely verbal thing. So just listen carefully. I want to give you some guidance or some guidelines for finishing the coursework off. And as you all know, you have 4 questions, and they are due to be completed, I think, in about 8 days' time or something like that. And I'm not absolutely certain how you're supposed to submit it. I think you've got to submit it to what used to be called Moodle. I mean, Pharos. It's just a lovely symbolic name for the new virtual learning environment system. So the first question was really asking you quite a lot about the principle of locality. And you will recall that the principle of locality has 2 forms, and I want you to state those forms formally. In other words, be as rigorous and as clear as you possibly can. Let me know that you do actually understand what those 2 forms are. And then, as a sort of a slightly separate but easier, hopefully easier task, I want you to explain it carefully using your own words. So to help you a little bit, there are just 2 forms of the principle of locality. It comes in 2 versions, one concerning space and one concerning time. And both forms are actually expressed in terms of probability. And here is an example of what I'm talking about. Here's a fairly formal statement of the spatial version of locality. It says, if there's an event Z which is taking place in a particular locality L, then there's a relatively high probability that event Z is also taking place in locality L1, where by hypothesis L1 is close to L1 according to some metric, some spatial metric, or maybe okay. I mean, the example I gave you from everyday life was not a computing science example, although I have actually illustrated the spatial form of locality in programming terms. I think it was to do with the processing of an array. So check that example out. But the example I actually gave you from everyday life was, I think it was snowing in Bond Street, and therefore there's a very high probability that the event, i.e. it's snowing, is actually occurring in a place nearby. And the place nearby might be 300 metre ways in the form of Mandeville Place. That's where the IFG is based. So, okay, so I'd like you to again repeat all this for the temporal version, and be as clear as you can about what the significance of this very general principle is. And again, in part B, I'm going to ask you to give me 4 practical non-computing situations where you make it clear whether it's locality to do with time or locality to do with space. And I gave you lots of daft examples, like as far as spatial locality is concerned, temporal locality is concerned. One example was, well, you're actually smiling at time t. It's very highly likely that you're still smiling at time t plus delta, where delta is a very small unit of time in the future. You will be, you don't, your smile is continuous over a small interval of period. So think of 3 or 4 or 5 examples where you can convince me that you really do understand locality. And okay, so the next part of the question is more challenging, because I'm asking you what relevance the principle of locality is to the success of using cache in our simple computer architecture. Why would we get a speed up if we used cache? Why, and what is the relevance of locality to that? I want you to tell me. It's important, right? And of course you can say a little bit about what your understanding of cache is. It's a high-speed memory that typically is very close to the CPU unit, and it's close in speed to the operations of the CPU. So, for example, if the CPU is capable of executing 1,000 instructions per unit of time, technically it's best if you have a memory from which you can gain thousands of instructions per the same or nearly the same unit of time. If you need to get the next instruction that you need from slow main memory, it's quite possible that your computer unit, your CPU, will have to stop processing in order to wait for the arrival of the next instruction. So it's important to be able to put what is likely to be needed into your cache as soon as you can, so you can keep the CPU fed with data and instructions. So I want you to look at the documentation for cache and to give me an expert analysis of the relevance of the principle of locality. Right. And the fourth part D of the very first question is, you need a cache controller to make all this hardware work together. And I'm going to show you the diagram in a moment, and to explain what you need to think about. So I'm going to move on to the second question, where I'm asking you to define a Python function which performs integer multiplication by means of using a while loop. I want you to write the program. and I want you to know how to input two numbers, and then to use the print operator to display the return value of the calling function. So hopefully, you're going to find that fairly straightforward. And definition of multiplication, well, I've done it and it works, and including the def mult reserved word def, all the way down to the return statement. I've got 1, 2, 3, 4, 5, 6, 7 lines, and then a print statement. Okay, and the next example is very, very similar. To multiply a number n by m, all you have to do is to add n to n m times. That is equivalent to n times m. So the second question is, how can you define a function that raises a number to the power of y? So, for example, you could plug in the parameters 2 and 10 to give me 2 raised to the power of 10. How would you do that? And the only thing you need to be aware of is that the code differs very, very slightly from that for addition. But the definition of raising a number to the power really comes down to the fact that you're going to multiply a number by itself m times. So if you're raising n to the power of m, you want to multiply n by n m times. Okay, and just make sure you look at the initial values of the variables that you set, and to get a few more marks, please give me screenshots of the two running programs so I can actually see that you actually put some work into using Python. You know how to use Python, you know how to define a function, and you understand a little bit about multiplication. So the third question covers the area of mutual exclusion, and I want you to give a clear example of a non-shareable resource in computing, and maybe a couple of examples drawn from everyday life. And the silly examples I gave you, which I probably won't accept. I mean, it's like two people attempting to sit on a chair. It's not physically possible for two people to be comfortably sitting in the same position on a chair. A chair is a non-shareable resource. Okay, just as the space that your left foot or your right foot or your leg is occupying is not shareable with any other foot, leg or physical object. It's impossible. Is it physically impossible, or is it logically impossible? That's for you to think about. So, and that leads us to, and I want a decent, I want you to think about, just don't list circumstances. I want some kind of analysis and explanation of why the resource that you've chosen is actually unshareable, and what would happen perhaps if two people or two objects tried to access it at the same time. And an example from computer science clearly is something as simple as a 1-bit memory cell. You can't have two programs or processors attempting to write 1 and 0 simultaneously, because it's anybody's guess what the result would be without some kind of control. Do you get a 1? Do you get a 0? Or do you get garbage? It's not clear. So I want you to then define what you understand by a semaphore, and how a semaphore can be used to gain mutually exclusive use of a logically unshareable resource. In other words, can I make sure that if I'm using the resource, nobody else is? Put very bluntly. Right. So give me a definition of a semaphore. And a semaphore is a special variable in the sense that it's binary, so it can only hold a 1 or a 0 in general terms, and show how a semaphore can be used with two operations, wait and signal, so as to gain mutually exclusive use of the resource. And if you can express the two operations using Python, that's great. That's great. And if you check all your notes, look at your notes and do your best to understand them, and you can actually now think about how two processes, or in common or garden terms, two people, could actually use a non-shareable resource without killing one another off. I mean, by using wait to get hold of to get control over the resource, and then to release the resource after you've finished with it, giving the other person or process or thread the right to access the non-shareable resource. Okay, so give me an example of maybe one or two resources that you can be shared simultaneously by more than one user or process. What sorts of things can be used at the same time? What do you think? Everywhere in the world that we look, there are shareable and non-shareable resources. So, the next part of one of the questions, you've got the code for two processes, P1 and P2, and I think you've got to look at the code and study it and convince yourselves that P1 will never execute CS1 at the same time as CS2. And the code for P1 is while T is 2, do absolutely nothing. Just wait, literally wait there. And when T becomes 1, I guess, it's not 0, it becomes 1, P1 will execute CS1, which is code to access the non-shareable resource. Then immediately finished using the resource, it sets T back to 2. And if you have a look at the code for P2, it means it's giving P2 the right to use CS2, to execute CS2, which is code that's going to be used to access the non-shareable resource. When P2, what P's doing, it's waiting for T waiting whilst T is 1, do nothing. But if you have a look at P2, eventually it's going to set T to 2. Therefore, P2 will be able to execute CS2, its critical section. Then it sets T to 1. It's giving the right back to P1. So my question is that the program 2 looks as though it guarantees mutual exclusion, because at most one of P1 or P2 will be busy executing their critical sections. But the solution is flawed, and can you tell me why? What's the problem? Well, if you do a little bit of research in my notes, you'll probably find a solution to that question. The last question is, well, tell me about what the essential components of a computer system are. And remember, we looked at a very simple computer architecture. So I'm not really expecting an answer given in terms of advanced components like RAID architecture, RAID memory architectures, or anything else. I just want you to tell me what the basic essential components are. like buses and registers and memory and a controller and an accumulator register. But you need to tell me how each relates to everything else in the system. What does it do? What does each element do? What's its role? What's its purpose? How does it operate together? And it's not quite. Yeah, I think it probably. The second question is, tell me what is meant by the fetch, decode, execute cycle. So you've got a computer, and you've told me what all the components are, hopefully. Now I want you to explain what it is, what's meant by a computer fetching an instruction, decoding it, and then executing it. And we studied all that in topic 1. And I'd like you to look at what I call the exploded view of the CPU, which is reproduced on the assessment paper. And I want you to almost like put numbers on it, like step 1, this is what happens, and show what happens. Step 2, this is what happens, and so on. And I think I've put a video clip to try and explain the fetch execute cycle on Moodle. I think it's a video, or it could be I don't know. It could. Yeah, I'm sure. I'm fairly sure it's a video. All right, and have a look at that, and that should help with this more challenging question. But the last question is, I've given you a table of opcodes. So, for example, an opcode for the instruction to halt the computer is 0, and the instruction to add data from some memory, some location in memory, fetch it and add that datum, fetch that number from main memory and add it to the number into the accumulator. So the opcode has got a decimal number 6, so the binary number is 110, and the instruction is going to be 110 followed by the address of a memory location. Right, so looking down the instructions I've given you, I've got a 110, so it's a second computer instruction. 11000000111. What that means is fetch the number whose location is 111 in memory, bring it back to the accumulator. Sorry, bring it back to the ALU and add the number in the accumulator to that number you've just fetched, and then add them together and leave the result in the accumulator. That is the meaning of a 110 instruction. 11 instruction. Add data. Well, I mean, very briefly expressed, it's add data to ACK. But what I mean is add the data found in a particular memory location specified to that number found in the accumulator and put the result into the accumulator. Okay, and what about the 000? That's the easy one. It just means halt the computer. Finished. So the program does involve, as far as I remember, adding 2 numbers and then storing the result back into memory. So it's good for you to be able to understand this low-level program. I mean, if you think about it, have a look at the program again. It's just a sequence of, each instruction is a sequence of 8, 9, 10, 11 bits. And the first 3 bits is an opcode. The rest of the binary sequence is a memory address. Okay, so I hope you enjoyed doing all this, and I hope you put a bit of hard work into it. And again, let me anyone uh, whether at home or Nigeria or any one of all the other countries that you're working on this. If you have any queries, just email me at chris.kinberg@intfoundationgroup.co.uk. No problems. And I'm going to finish with showing you. So I'm just going to try and find one document I've got. I think it's called document 4. And this is this horrendously complicated looking diagram. It's actually a diagram that you've seen before, and you might not have taken very much notice of it. But I want you to understand that everything above this red line represents, in fact, the computer architecture that we studied in topic 2, I think it was. Topic 1 was the hard disk. Topic 2 was computer architecture. So in topic 1 we looked at the computer, the CPU, and a couple of other bits and bobs. And it has 2 buses, an address bus and a data bus. So the thick black line here is the data bus, and it does actually connect to the memory data register here. And the address bus, which is not terribly clearly marked, is this line here. It's this thin black line here. And what the CPU can do is to put an address into the memory address register, the MAR. So logically, if the CPU wanted to write data to memory, what it does is to put an address in the address register. It puts some data into the data register, and then, which is not clearly shown, so I haven't actually shown it, the CPU will tell main memory to do a write. So I'm putting this data into main memory at this address, putting this data into main memory at this address, and a couple of units of time later the operation will be complete. And likewise, if the CPU wants to do a read, then it's going to do exactly the same thing. It's going to put an address into this register. How does it do that? It puts it onto the address bus, and it's going to leave. It's not going to put anything in the data register because we're doing a read. So it then tells the main memory to do a read, and a couple of units of time later, the memory read is actually going to be put into this data register, which is connected to the data bus, enabling the CPU to transport the data back to the CPU where it's needed. Okay, so what we've done is to add some hardware. Here it is, the cache memory. And I want to argue that we need something like a controller, some control box of tricks that will enable the CPU and the memory and cache to cooperatively work together. And I'll explain how it does it. So I'm talking about the cache interface controller now. One of the things it's responsible for doing is to intercept a read signal, a main memory read signal from the CPU, and it's going to say, okay, the CPU's asking me to read memory. So I'm assuming that the CPU has already put an address into the address register, and I'm going to send the memory a read command. Okay? But at the same time, literally the same time, the cache interface controller is going to ask the cache by means of I don't know, something like a check command, whether it knows anything about the address in this register. And as quick as a flash, in a tiny proportion of the time it takes the main memory to complete its read operation, the cache will return either a hit signal on the hit line or a miss signal on the miss line. And the significance of a hit is, yes, I've got a copy of what you're asking for already. So CIC, if you want to, you can completely ignore the memory and simply tell the CPU that the data is already to be found in the memory data register, because I'm going to put the data that I know something about. I know it's associated with this memory address. I'm going to put it into the database. And as a result of that, the CPU can pick up the data in the data register very, very quickly, compared to the time it takes for slow old main memory to finish reading data out and putting it into this register. And you might say, well, okay, that's all very well. I understand what's going on at that level. But how does the cache ever get to have a copy of the data being requested in cache? How does it have it? How does it happen? Well, I'll tell you. Let's just repeat this sequence of events. The CPU is just starting up. It wants to read, say, the first instruction or the first item of data that it needs. Puts an address in the address register, and at the same time that it's asking main memory to do a read, it's sent a check signal to the cache. Do you know anything about this particular address? Have you got a copy of the data associated with this address? And the answer is going to be no. So what happens is the kick patiently waits for main memory to put the data requested into the main memory the memory data register, and at the same time, on completion of the read, it's going to make a copy and put it into cache. And the reason for that is that, let's suppose in the near future, the CPU needs the same data, so it's going to put the same address here, and it's going to wait. The system's going to wait until the memory is being read, and at the same time, the kick's going to check to see whether cache knows anything about the contents of the memory location just requested, and at this time, the cache is going to reply to the check request with a hit. Yes, I've got a copy. Forget about reading main memory. I've got a copy here, ready and waiting. You can use it. And so the CPU will move the data from this register back into the CPU. Okay, and of course, all these data movements are going to be under control of the main controller in the CPU. But the cache interface controller is working on behalf of the CPU. If you like to think of it, it's intercepting the CPU commands and acting on them. What does it need to do a read? Well, one thing, check cache first. That's important. And I think when I originally spoke about cache, I said that the access speed of main memory is something like 200. You know, the example, just for the sake of argument, was it takes 200 maybe nanoseconds or milliseconds to perform a read. But to actually get data out of a cache takes an order of magnitude less. I mean, 50 nanoseconds or 50 milliseconds, or like an order of magnitude faster. And I remember quoting the IBM research to you, and saying that even if you've got a very small cache, the probability of finding the CPU finding data it next needs, or the next instruction, is going to be 75%. There's a 80% chance of finding what you need in cache, because in the past you've had a run of misses, but in the future, if you've got the data that the CPU needs, you're going to get a run of hits. And the big question is here, well, what makes this system work? What does how can you successfully and reliably fill cache up with what's needed by the CPU? Remember, the cache is going to be much faster than main memory. Well, the answer is very simple: locality. It's the principle of locality. It says, once you've used something, there's a probability that you want to use it again in the near future. And that's exactly what happens. 75% of the time. The CPU will get what it's looking for in the cache. It can bypass accessing main memory. Okay, so I think I'll end it all there. We did. Oh no! One other thing, just for completeness' sake, I want to show you. Let me see. To show you this document, just for completeness. I've just got I want to spend a few more minutes on handshaking, a little bit more on handshaking, and I've shown you a very complicated set of waveforms representing a full handshake. I'm just going to summarize it here and just explain what's going on here. So intuitively, I can talk in terms of holding out my hand for as long as it takes for you to see it, because maybe I'm actually raising my hand and dropping it so quickly that there's no way you could possibly have seen it. So I'm just going to hold it out for as long as it takes for you to see it, and you will see it eventually. Right, so from a logic point of view, I can send you a request by changing this line, this signal, from 0 to 1 and keeping it at 1 for an indefinite amount of time. I just want to tell you that I want to talk to you or want to ask you to do something. And you will do the same thing when you see my hand. So at some time I send my signal to you at this time red dot and keep it at logic 1. And a short time afterwards, at time t plus delta, I'm actually going to inform you that I've seen your signal by raising my acknowledgement signal to logic 1 and keeping that high. I want to make sure that you see my acknowledgement as well. And in between, when I send you a request, typically what I'm going to do is to get some data ready to send to you, and on receipt of that data, you will process it and give me a reply in the form, perhaps possibly, of a computation on that data. Maybe I'm giving this hardware unit meteorological data about pressure systems, and what I want back by way of an answer is what the weather in London is going to be in the next 2 hours. And when the second machine has completed has responded to my request, it acknowledges that fact. And at any time after that point, I can take the data, and as far as I'm concerned, you've replied to my request. So, I can put a couple of diagrams, the third and final step, together. I mean, I can send out the request, keep it one for quite a while, and the other machine is going to send me the signal and keep it on so that I can actually see it. When I do see it, my way of telling the other unit that I've seen the acknowledgement is to lower from 1 to 0 my request. And this will actually cause the other machine to drop its acknowledgement. Drops its acknowledgement. So the fact that I've dropped this and the other machine drops its acknowledgement, seeing that communication has been successful and we have synchronized successfully. I want you to, what this represents is that you lower your hand when you see my hand fall. This is my hand falling. You lower, this is your hand. You're lowering you're dropping the signal, dropping the ACK signal, changing it from 1 to 0. And you let me know in this way that my signal request has been seen. I mean, I think this should be has been seen. Okay. And I've just got, believe it or not, I've just got one other document, if I can find it. I'm just going to show you. I've shown you this document before, but I want you to understand what it means for one system not to be able to see another system. And this is the document I'm referring to. Where's the diagram? I'm just going to focus on this diagram. So graphically, what's called the synchronization problem arises when machine A, so this signal here is being sent by machine A, and it's sending me a very narrow pulse whose length is TP. It's the pulse length of this signal. So it's very narrow. It doesn't last for very long either. So this is me here. I'm the receiving system, and this is my clock. Nice regular clock, tick tock, tick tock, tick tock. And the key thing I want to point out here is that this system here can only see this signal if this bit of the signal occurs whilst this system has a rising clock edge. I can only clock in this logic 1 if the signal occurs at this point in time. But the pulse occurs way beyond the rising edge, and therefore I'm not going to see it, in the sense of I'm not capable of remembering this. Well, the answer to the solution to this hardware solution to the synchronization problem is simply to make sure that the clock frequency is greater than 1 divided by TP. When this doesn't hold, I'm not going to be able to see the short signals that you send me. Okay. I mean, you don't know that I can't see you. You're not going to alter the shape and size of the pulse with which you're sending me data. But possibly what I can do is to increase the frequency. Remember, the frequency is really the length from one falling edge to the next. I can increase the frequency by making this distance much smaller. And I mean, let me shrink this a little bit in the way in which I want to. I'm just doing it so I'm getting a sort of minimal shrinkage. So I've got this clock's going to go from 1 to 0, then it goes up, and then it goes down. So instead of going down, then going up, and then going down, I've made it fit. I've made it equal to, the distance here is going to be equal to or less than TP, which is the distance between this rising edge and the falling edge of the incoming pulse. I mean, all that pulse means is 1. I'm just getting a 1, but it could be a 1 sent to me by a deep space probe saying, look, I need help urgently, help. Just a single bit could be an emergency signal, and it's very important I see it. By shrinking, let me just make that look a bit more proper. By increasing the frequency of this clock, I get this rising edge occurring during the pulse being logic 1, and I will be able to capture that. I will be able to capture that in one of my memory cells, and I can then do what I need to do with it. So this might sound horribly complicated, but the general problem is if I've got 2 hardware units, A and B. Whoa, that's a strange one. Got A and B here. Got A. God, I find it very difficult to write with this. That's B. I've got 2 systems. The question is, how can I guarantee that A can talk to B? I mean, B might be much faster, and it will always see a signal if I send it to B. But when B sends me a signal, there could be an issue if I'm much slower than B, for the reason along these lines. When the signal comes into A, I'm going to miss it for exactly the same reason, that it doesn't correspond with a rising edge, which always means I should be able to clock it into a flip-flop or a register or a little memory cell. And finally, I mean, sometimes it's not possible to perform this, to get this kind of solution where you can arbitrarily increase the frequency of a system clock. And sometimes there's all sorts of technological problems preventing that. But there's a solution to that. And this kind of system is a hardware system. And what's coming in here is, maybe a very short pulse. I mean, it goes from 1 to 0. 0 to 1. This is the pulse here. Well, using this system, and I don't want you to go into this very much, but I just want you to realise that there is a mechanism that will allow you to synchronize systems. When this pulse comes in, this output will stay at 1 until you until you reset it. So this is logically, this is a very small pulse system which is easy to miss. But this little system, which is called a ones catching cell, will result in this being logic 1 for as long as you like. And that means is that when I clock it, when I put the clock in, I can choose a clock frequency, which is quite some reasonable frequency, and I can capture that. And at that point, the data will actually stay, the 1 will stay on the Q output here. So that there's an alternative. And I think a full handshake is a sort of substitute for this kind of system. And all I'm doing is, if there are two systems and you don't know anything about their relative speeds, in such a way that it's going to be very, very difficult to get these two systems to communicate, you can use a full handshake in the way in which I've just spent the last quarter of an hour explaining. So hopefully there's something of interest here, and I'm just highlighting some of the important points that I've already mentioned, but I'm just drawing your attention to. It's got nothing to do with coursework, but you've got this recording to refer back to if you need to. Okay, so thank you very much for listening. Just a comment on attendance at Friday's presentation is that I think 4 people weren't present. So hopefully this document will be of some benefit to them, and it'll be perhaps of double benefit to the people that actually turned up to my Thursday class. So best of luck. Don't forget, you need to pay attention to where you send coursework when you submit it. There's some talk about students being required to submit it to Pharos, but at the moment I don't know very much about that, but we've got a week or so to go. So all the best, and take care of yourselves. Goodbye.